So maybe I would like to ask you how you'd like to define yourself, or maybe people first time listening to you. How would like to define yourself? Yeah.
I'm currently a faculty member at Duke University in the Electrical and Computer Engineering Department. And for a long time, I've been studying metamaterials, really since around 2000. That's what our group does here at Duke. Also, at the same time, I've done a lot with metamaterials commercialization. So I'm also involved with a company called Metacept, where we're looking to commercialize metamaterials to spin off new companies, and that's also been part of my interests.
Interesting. So maybe before going to more about invisibility and using multi-material metamaterial here, what is metamaterial? If you can just to give it a basic definition, and also the challenges in the scope of the metamaterial here. Yeah.
Well, to start with, what a metamaterial it's a very semantic sort of argument for what is really a basic concept. The original idea of metamaterials, when I first started thinking about this around 2000 or a little before, was a way of mimicking what materials do in nature, mimicking the molecules or atoms of conventional materials with artificial structures. So things that are not microscopic but are like constituents. So you imagine a bunch of pieces that all look the same and assembling them together into a material, with the material properties defined by these inclusions, these macroscopic elements, rather than atoms or molecules. So it's really a way of creating a material with certain properties related to the geometry of the elements rather than their chemical properties.
Mm-hmm. I really like this point. Maybe I want to ask you when it comes to creating new material, which you mentioned here, how do you see the material and the geometry? Because to be honest, I would like to know how geometry here could so much game changing in the performance of the material. Can you give an example, the material and geometry architecture? And from your experience here, which one was more intriguing to you? Of course, the material is interesting here, but I mean, giving up something very interesting or not, yeah, when it comes to utilizing metamaterial here.
Initial thought behind metamaterials was for us in the electromagnetic space. So we think about electromagnetics or optics. And the optical properties there that you think about, or we originally thought about, were the one that most people know is the index of refraction. That's, light hits a surface into a material and bends in the material a certain way, and that's related to the index of refraction. That index of refraction is responsible for things like glasses, right? These are made of glass, and they bend light in a certain way. Deeper than that, light is an electromagnetic wave. It has an electric component and a magnetic component, and you can control those each separately. So there's two other parameters that are of interest, and that's called the electric permittivity, which is often given the Greek symbol epsilon, and the magnetic permeability, which is often given the Greek symbol mu. So those are macroscopic parameters. If I give you a piece of glass, I can tell you what its epsilon is, its mu is, and its index of refraction. You know that glass is composed of billions of molecules or atoms, but you don't care about those because you do an averaging over those to get those properties. What the concept of metamaterial is that you don't have to start with atoms, but you can start with little objects of some sort. And those objects could take the place of atoms and give you that same effective parameter, the index or epsilon or mu. So what should the elements look like? It turned out that it could be very simple. It could be just a little piece of a smaller piece of glass that's shaped in a sphere or a cylinder or something that's much larger than an atom, but much smaller than the wavelength. That would do it. But what we found that turned out to be pretty useful was little circuits. So little things like rings and wires would give you this response. You could engineer a wire to have a type of electric response and give you an effective permittivity. And you could have a little loop, almost like a little electrical circuit, and that loop would give you a magnetic response. Both of these things were thought about by Sir John Pendry. Just in the 90s, he started writing about these ideas, and we were very inspired by that. I was inspired by that. So this concept of arranging wires and loops of wires into different patterns to make different materials with different properties is really the origin of what's sort of the modern metamaterial concept.
Great. So when it comes to negative fractions here, can you tell us about how the story when you started to get the experiment and now we speak about invisibility? Can you explain what's actually happening here and why it's happening if we don't have a background here? Can you elaborate more?
Right. So so negative index and the invisibility are two different pieces of the puzzle. They're different types of response. Negative index is a funny one. It's an index of refraction that's negative. And that means if light hits an interface to a material with a negative index, it bends the wrong way. Instead of bending towards the normal, it bends completely on the opposite side. This was a material that was hypothesized by Victor Veselago in the 60s, but it was just a theoretical conjecture. It requires that the electric permittivity be negative and the magnetic permeability be negative. So I've mentioned those three parameters. The index is the square root of epsilon times mu. In most every material that's known, epsilon and mu are positive. But you can create a material where epsilon and mu are negative, and a negative times a negative is a positive, which means that you have a square root of a positive number, but it turns out you have to take the negative square root. Negative square root of 4 is either plus or minus 2, for example, and it turns out that when epsilon and mu are both negative, you have to take the negative. So what does that mean? What that means is it turns out that these materials are resonant. You have a resonance built up in your little element. And when you have that resonance, that's the key to everything, because you can get a response which is completely out of phase with your driving force. So if you imagine the optical field is moving electrons around, and most materials, when the field goes like this, the electron follows it. If you have a resonance, it doesn't violate anything. It imposes some conditions, but you can have this weird situation where your driving field is like this and your electron's going like that. And that's what happens in a negative material. So you have, for both epsilon and mu, you've got the effective particles running the opposite way from the direction that the field's applied. That seems weird, but it's all to do with the resonance. So if you imagine what happens when you push a child on a swing, for example, if you push if you push very slowly, you sort of push, the child comes back, and you push again, and the child's moving in the direction of the force. You push a little faster, you hit a resonance, and all of a sudden it takes very little effort, and the swing keeps getting larger and larger. If you started pushing out of phase, in the wrong phase, all of a sudden what happens is that the swing is moving back to you when your hands are outstretched, and it's as if the force is against you. But that's all because of the resonance. It doesn't violate anything. It just is a weird thing because you can build up energy in the system. And so it's a deep concept. It confused a lot of people. I wouldn't be surprised if you're confused by that. But the result is that you can have these parameters become negative, and that was something that just wasn't exploited or thought about very much until we started doing these experiments around 2000.
Mm-hmm. So when it comes to using this an application like stealth technology, for example, or invisibility cloak here, you mentioned there's something interesting regarding relativity, and you can explain more about what do you mean about maybe explanation could be related to relativity here.
So you're switching to a different topic now. So in the metamaterials community, there was a lot of interest in, negative index is one interesting thing that had never been seen before, and so there was a lot of after that discovery was made or reported, what else can you do with metamaterials? And one of the ideas that my colleague Sir John Pendry came up with was thinking about this idea of designing materials by first considering a coordinate transformation. So you can take, one way of designing things. There's a whole way of designing optical devices. Of course, there's refractive optics, there's gradient optics, and lots of tools. But one thing you can imagine is if you were to draw a bunch of light rays on a piece of paper, and then you were to distort that paper. Imagine it was on rubber or something, and you could just move it around. You could bend those rays just however you wanted to. You can't do that in real life, but you can take that, what's called a coordinate transformation, and you can write down mathematically what you did, and you can apply it to Maxwell's equations, which govern light and electromagnetic waves. And that results in giving you a prescription for the electric permittivity and the magnetic permeability that achieve that exact thing that you wrote down, that you just sort of did in your mind, right? So if you want to make a cloak, what you'd want to do is sort of open up space, push all your lines away so that they kind of went around this region, and then on the other side they'd be unperturbed, right? You've just disturbed it in the center. And in the center you can put whatever you want to be hidden because the light never sees it, it goes around it. And in so doing that, we ended up with a prescription for what sort of material we would need to achieve that. That is what led to the cloaking demonstration. It's a certain way of doing it to achieve this phenomena of invisibility. Where it relates to relativity is if you had the right combination of masses, and it would really take a horrendous amount of energy, but it's the kind of invisibility that Star Trek, for example, imagines in their universe. Mass can warp space. So if you have presumably the right combination of masses or energy, because they're equivalent in Einstein's world, you would be able to actually physically warp space so that you could take your ship or your whatever you want to hide and just take it out of that space, and everything else would look unperturbed. So you would it would be removed physically from that space. You'd warp it such that light and everything else would move around, but it looked as if it had been unperturbed. We can't do that with materials. We can do this illusion of invisibility. We can apply the same sort of coordinate transformation, but again, it involves a resonance. And when you have a resonance, it means you can only do that at one frequency, or a very narrow band. So inherently, what we did experimentally is has a lot of ties to this relativistic approach of invisibility, but it's not changing the physics, right? So all you're doing is doing this effect at a narrow band of frequencies. So as a stealth technology, it's not very good because it's only going to work over a very narrow band.
Mm-hmm. That's a good point. Maybe I'll ask you two questions here about the design, how you design invisibility for different frequencies. If it's in tiles, materials, metamaterials, it's actual in the material level, or a structure and geometry here for different frequency. Maybe the first part here.
Right. So there's a few answers to that. If you have this prescription, and this prescription is given for a given frequency, and if you deviate from that frequency, it works less and less well, and very poorly if you go very far from that. So your design is specific for a frequency, and if you were to think in concrete terms what that looks like. That cloak, for example, the one we did in 2 dimensions was sort of a cylinder, kind of a plate, a bunch of rings around it, each ring having a bunch of metamaterial elements, each element designed to give you, the response that you needed, both electric and magnetic at that point. So if you wanted to do that for multiple frequencies, it's not clear quite how you would do it in a passive material, because each one of these has to be resonant. If you tried to overlay 2 different ones, the ones that were off resonance for one frequency would cause problems at the one that you're trying to cloak at a different frequency. The way around this is to introduce energy into the system. So actually power each point using active material. That has really not been worked out very well. I mean, it's known that you can increase the bandwidth that way to some extent. Really not infinite, but to some amount. But how you do that is just an open area of research. I mean, it's theoretically possible, but I don't know anyone that's actually done something that complicated. And once you start putting energy into a system like that, you have instabilities and all sorts of things to worry about. So it's a hard problem to solve. What's intriguing is that it's possible that it should be possible to do something like that, but I think it's very difficult right now.
Mm-hmm. Maybe also ask you about your stealth technology, invisibility, and especially when you speak about the aircraft, for example, that's a case of that. And then there's anti-stealth technology, and then anti-stealth technology. And you see it's going in two direction, how you be visible and detect the visibility, and then be visible. And it's going to now anti-stealth technology. But I don't know where it's now, but I'm curious about you, about the design, when you design about visibility and how to detect you, and then be visible again. I don't know if you get what I mean, but it's a scenario.
Well, there's invisibility is an interesting concept because most of the world is invisible to us, right? We see in the optical wavelengths. When you're talking about stealth for the military usually sees with microwaves. So it's a big deal to understand the visibility or invisibility of things at microwave frequencies, which is where we did a lot of our experiments. So traditional stealth, this idea of warping space, having waves come in and then being rerouted so that it looks like they pass through free space, is not something that's part of stealth technology because it's just really difficult to do. It doesn't pass through materials. So stealth has typically been based on absorbing the waves that come in or rescattering them, which is why if you've seen pictures of some of these stealth planes, they look so sort of angular and strange because they're really trying to either scatter away the return signal to a radar or absorb it. So if you imagine a radar which is sending out a signal and then looking for the return, the stealth technology is pretty good if you just absorb everything. If your radar station never receives a return signal, this is invisible as far as the radar is concerned. Where that breaks down is if you have another radar station over here, which is working with this one, because it's really impossible to absorb everything. And even if you don't scatter back to this first radar, if this other one can detect the scatter radiation, then you have effectively made it visible again. So that's kind of the cat and mouse game that's being played in that field. You having a low observable structure it works if you're just sending and receiving pulses from one direction. But if you're looking at multiple directions, it's very hard to cloak something like that. You'd have to really absorb everything, and that's hard to do. That's invisibility, in that context. Another one that we've spent a lot of time thinking about is in security imaging. When you go, for example, pass through a scanner at an airport, RF is used to see things on a person because it can see through clothing. So you can look for threat objects, you can look for guns and knives and things like that. So that's a good example of rendering something invisible to the wavelengths of interest and looking for something. Is there a way to defeat that? You could imagine that there's ways of making things less observable as well. And that's another cat and mouse game that's being used. You wouldn't necessarily call it stealth, but you'd call it invisibility versus invisibility, visibility versus invisibility.
Mm-hmm. Maybe I want to ask you, do you think of any example in nature, maybe related to invisibility and maybe inspiring that design? Do you have any examples from nature that's really good example of visual invisibility here, if we speak, and you think it could be interesting?
There is, and most of it comes under camouflage, right? So invisibility is really about detection. If you can't detect something, it's invisible to you. And so there's a lot of animals in nature that can change their appearance to match into their surrounding. And that's just as good an invisibility trick as any. And it's really remarkable. There's certain things like cuttlefish that are known that can really change by chemistry, I guess. I don't know their full physiology, why they're able to do this, but they can change their color and actually patterns to blend into their surroundings. Also, certain types of lizards, things like that. And that really is a useful form of invisibility in the sense that if you can't see it, you can't see it, right? Or if it's hard to see, if it reduces or obscures your ability to see the target, that's just as valid a route to invisibility. So, given the difficulties in some of the types of things that we do at optical wavelengths, it would be a perfectly reasonable approach to try to mimic that, what nature does, by projecting what's behind you in front of you so that you blend in very well. And I think there are schemes like that. I don't know how successful they are, but that's certainly an idea that is reasonable.
Mm-hmm. Maybe I'll ask you, there's something still, you mentioned there's a lot of things to be solved, but what maybe still challenging part here or limitation when it comes to understanding, designing visibility for maybe like a visibility cloak, for example, completely? What did that mean, do you think, to achieve that?
The difficulties are really significant. One is there's for electromagnetics, the speed of light is what sets that bandwidth limit. So we're not going to get around that. If you want to see something in air or near vacuum and make it invisible, that is really going to be difficult to get around those fundamentals. The only way around that is maybe make the material active. And again, that's a whole area in itself for study. There's a lot of new science that has to be developed there to make that work. We understand the prescription. We know this is what you need, but to get that and to make it broadband is really a major challenge. Another possibility is to look in areas where where it's easier, where that fundamental limitation of the speed of light isn't there. So, for example, if you were to image something in water, water has a high dielectric constant. The speed of light is slower, but it's the speed of light in the medium that matters, and so that actually enables you to have a broader bandwidth of cloaking. This was something that was shown by Martin Wegner. He did an experiment in a medium and showed that you can have much more broadband cloaking, and it's very interesting. Also, acoustics doesn't have that limitation, so if you wanted to make something invisible in the sense of sound waves, that is something that is worth exploring, because I think there's more possibility there. And that also has potential uses. The strict invisibility in air of making something disappear to all wavelengths is an incredibly challenging problem.
Mm-hmm. Great. Maybe I want to ask you, there's a critique you received regarding working in this problem. I don't know that critique or people disagree with what you're doing in it comes to invisibility or this particular use of metamaterial here.
No, we had a lot of controversy early on in negative index, because that was such a weird physical property that it struck people as very counterintuitive, and so a lot of people doubted it could exist and doubted everything. But after a few years, I think that was settled, and that was done. So by the time cloaking came around, we were... So one, I didn't expect it would be such a large deal. It was just a scientific thing, and it really captured the imagination. So a lot of people just liked it. It happened to come out around the same time as Harry Potter, so there was a lot of tie-ins with that. It's just a topic people like, and I think most people understood that we were doing an aspect of invisibility, but it really had a lot of limitations, and we were very clear about the limitations. It's interesting from the design point of view. Transformation optics, the way you do this, has a lot of other applications, and that really took off as a field. Really, thousands and thousands of papers now have been written about transformation optics that are not all about cloaking. But cloaking really, just from the scientific um, challenge, prompted a lot of follow-up work, and I think most of it has been very positive. It's just really a fun thing mathematically to think about and physically to think about. So it's really pushed that science of metamaterials in interesting directions.
Mm-hmm. Maybe before going to the other uses of metamaterial, about the design, if you can tell us about that, when you think about the design, because you work in now more than 20 years, the design space for metamaterial for invisibility, can you tell us just a glimpse what's so significant to you when you try to think about designing the structure to be invisible? What is in the design space is so significant or to help you to come up with the desired goal to be invisible here?
Well, the approach that of transformation optics that John Pendry helped come up with is really a powerful tool. So if you think of designing things by just warping space, that gives you a lot of ideas. And as a designer, you don't even have to think about what the material property is because it's given to you automatically. As soon as you know how you want light to behave, you just sort of write that down, apply it to Maxwell's equations. There's a little bit of work involved, but in the end, you just get this prescription for these elements that you need. We've had a lot of experience in looking at an epsilon and saying this is how you get it, looking at a mu and saying this is how you get it. So for us, if we're making a volumetric material that's going to try to do this, we know that if epsilon is this, we need a wire of this length or of this shape. And if we need this mu, we need a ring that looks like this. So that's all part of what we've sort of developed over the past number of years. And so, everything in my mind gets translated into a bunch of little wires and rings. Now you have to support those somehow. So a lot of what we do is make use of circuit board technologies. It's really easy, because you need thousands and thousands of these elements to just use conventional circuit board manufacture because they're really good at making little metal patterns on different types of substrates. So we look at that and we kind of think of how to assemble it, and that really becomes the basis for our metamaterial if we're thinking about electromagnetics. I have colleagues that work in acoustics, and so that design is very different, right? You're thinking about how you imagine an acoustic wave. You're thinking about pressure, waves, and velocity and mass, and mass density, and so all those sorts of things lead to very different sorts of designs. And they've developed their own intuition for making acoustic metamaterials. But that's basically how it works.
Mm-hmm, great. So since close then I have a question, maybe if you can tell us about other application for metamaterial. You have already, I think, spin-off companies here, but maybe you can give us very critical, a very crucial application for metamaterial when it comes to industry here. Yeah.
I think we've done a lot of work in antennas, and the revolution in antennas really happened I'd say it started happening in the 90s because wireless really took off. And at the time, once wireless takes off, you start to need antennas. And antennas that sit and just have, one direction in which they look are really not consistent with the entire revolution that's happening where things can be anywhere. So you want an antenna that can actually be reconfigurable and move and change its radiation pattern. You think that would be a solved problem, and it kind of was with things called phased arrays. But phased arrays are really expensive. They couldn't be just instantly accessible to consumers. They really cost hundreds of thousands of dollars, if not near millions, and they consume massive amounts of power. Metamaterials have sort of revolutionized that entire segment because we can make apertures that can create different types of radiation patterns, but with much lower power draw and much lower cost, and so things that can really go into consumer level markets. And so, if you ask where antennas are needed now, it's everywhere because wireless is such a key component in our lives. So it's communications, it's sensing, it can be things like wireless power transfer. All of those things now are just continuing to increase in their needs. And so we've seen metamaterials now be really useful in all those areas. And similar things, for example, LiDAR and other venues wherever you need to create an electromagnetic beam at some frequency and then receive it. All of that we found huge advantages with metamaterials.
Maybe I'm just ask you, when you have the idea to design, for example, the antenna or metamaterial for application here in industry, how do you ensure the idea could be commercialized? I mean, when you work in academia, still there's you try to think about an idea, but still you don't know the aspect of commercialization. How do you balance the two, that you make sure it's useful as well?
That's a good question. So how you balance or how you decide something can be commercially useful. We've got a lot of good friends in this. So something that happened early on is a company called Intellectual Ventures decided that they were interested in metamaterials back when it was controversial and no one knew what it was good for. And they brought this company was started by a man named Nathan Myhrvold, who's a former CTO of Microsoft, and they decided to take a significant stake in metamaterials. They licensed and started building a portfolio around metamaterials, and this was really before anyone knew what it would be good for. So they, coming from university, I had just done the basic science, not really aware of what industry needs were or applications. And they helped a lot with that sort of marketing. We said, oh, here's what we have, and working with them, they sort of put together a business development team, and what happens is now a conversation. You start saying, okay, could you do this? Because this would be useful for this, this, and this. When we started Metamaterials, it was a solution without a problem. We didn't know what we were making it for. Once we started getting problems, you begin to tilt your research more towards that, and eventually you meet up somewhere. And then you need people to go around and say, okay, well, if you actually made this, would a lot of people buy it? How much of an impact would it make? And all of that process went on over a number of years, resulting in the spin-off of 6 or 7 companies so far, and we're still considering more, that have actually been quite successful in their different technology markets.
Mm-hmm. That's amazing. Maybe I want to ask you about your vision, or when you try to think about what's next for your passion to design new metamaterial or the solving the invisibility problem, for example. What do you think about? What is your aspiration here?
One of the recent companies that we spun off, which is called Neurophos, which is very interesting because it is looking at doing optical computing. And it turns out that optical computing is something that many people are looking to achieve. But the real benefit is trying to do optical computing with low power consumption. So we have the same potential benefit with metamaterials, again, that would potentially allow us a scalable solution to do things like inference chips. So this is a lot of what's sort of happening now in the industry, where you're using a different type of computing to help with machine learning and identification. So, for example, in self-driving cars, you have a lot of processing going on in your car to figure out all the obstacles. If you want to have a self-driving car, it's got to be able to identify everything, make sure you don't get into a crash. All of that requires heavy processing, and the more this industry goes on, the more of the power budget in a car is used for this exact purpose. So there's a real need for optical computing, which can get around both latency, be faster, and also lower power consumption. And so we're looking at using metamaterials for that now with this company called Neurophos. And moving into a computing arena just completely enlarges the market for metamaterials massively and would have a profound impact. So that's one of the things that we're looking at very closely and hoping to have a positive outcome.
Mm-hmm. Great. Maybe I want to touch again about, we mentioned that we don't see the reality as it is, and I think it's related to invisibility. And maybe some voices can say that how you ensure that this something will be good for humanity if we have invisibility here, for example, clocks. And when you try to think about our life and just as a human, we don't see the reality as it is, and maybe some stuff are maybe invisible to us as a human because we have a limited, I don't know, sensation, maybe. But how do you think about that? Create something invisible, and yet we as a human, we don't know the full reality of the life. I don't know if you get to what I see here.
I think so invisibility to really hide something just does not seem to have a lot of uses except in a military sense or an espionage sense. However, there is as we continue forward in this world of wireless devices and things communicating with things, interference becomes a problem. And so if, even though we don't see with microwaves, all of our devices see with microwaves. Our phone sees at, 1.8 gigahertz or 2.5 gigahertz, and your laptop sees at 5 gigahertz and all that. All of these things now are communicating with each other, and so a lot of things interfere with that. Invisibility can be used to take those things that interfere out of the picture. And that might be potentially down the line a use and a really conceivable use for this type of technology, which is to essentially remove, not that you don't want to see them, but that you want to remove them from a communications channel or a path. I think that's something, or to reduce interference. That could be a good use of this technology.
Mm-hmm, great. I don't know if you have any advice you can give, or maybe you would like to share, maybe in the career or personally, you think is very important to you?
I think if you're talking about people that are thinking of a scientific career, I think if it depends what stage you're at, but always I think you have to keep learning. Everything that we did in the beginning with metamaterials, I was sort of amazed that everything I'd ever learned sort of came into play, that every tool that I picked up, everything, I ended up using. And so everything you sort of come across is really helpful, and you have to know as much as possible. So that's one thing. And two is I think it's worth always asking what use your research would be, and always striving to try to make it relevant, and hoping that it affects more and more people, because that's kind of what you're in it for, right? Bringing knowledge to the world is one piece, but after that, looking to see how it can be useful to people is another. And so that's something that I did sort of naturally, and I think it should impact whatever you're doing. I think that's just a process you can follow.
That's amazing. I don't know if you have any final words like to say here, to people listening. Any final words like to say?
No, other than that, it's been a very fun thing to think about. Not many people get to think about invisibility as in the way that we were able to. It was a fun endeavor, and all of the science that grew out of that proved just amazingly interesting. So, and none of this was started with any intent. All of it is just grew out of the curiosity of science. Negative index was never even a thing we thought about. We started sort of working and doing stuff just for the fun of it. So love what you do is certainly a message, because the basic science is why I was in it, and why the people around me were in it. In fact, when we started Negative Index, it was just a hobby. It wasn't funded. It was nothing that anyone probably even would have funded. We did it at nights and weekends in the lab I was in, and then suddenly it just turned out to be a big thing. So I would say, just make sure that you're pursuing your own interests and staying aware.